Hi everyone, hope that you're all doing well. In this lecture, I want to introduce you to confidence intervals. So some announcements that are specific to my class this semester. I'm teaching this at the UW as per usual. Let's get down to the plan for the lecture. So I'm going to introduce confidence intervals by once again reviewing the binomial distribution, and I keep coming back to the binomial distribution because it's a really nice way to understand what a sampling distribution really is. And you can actually derive the binomial distribution by hand with just a little bit of algebra 2. Admittedly, you have to make that algebra 2 work fairly well, right? You should be in full command of things like summation operators and the binomial coefficient that I've derived in these lectures before. But you can do it by hand without any super fancy math, and that's a really cool thing. So we want to have a good handle on the binomial. Then I'm going to give a brief micro lecture on 4 ways to get answers to binomial questions. So one unfortunate truth about the binomial distribution is that while it's relatively easy to calculate, say, exact binomial probabilities in cases where you've got a relatively small sample size, in a lot of cases where you've got a large sample size, you won't be that interested in an exact binomial probability. You might be interested in a probability for a range of possible values of k, the number of successes. And there's good theoretical reasons for this, but unfortunately that makes calculating these things by hand fairly tedious, not terribly so, depending on the situation, but enough that we should probably try to take some steps to expedite that procedure. Now that said, it's generally speaking still a good idea to understand methods for finding binomial probabilities that require you to understand what you're really doing so that you can use this tool effectively. There are calculators out there where you can basically just kind of plug in the problem and get an answer, and you don't have to really understand much to the problem beyond what n is, what k is, and so on. But I think the degree to which you actually have to use the formula in the calculation and just let the computer handle the pure tedium actually is going to help you understand what it is even better. And that's something that a machine can never do for you, by the way. So a machine can never tell you what the binomial distribution is really saying. That's something that you have to understand. And a general tendency in the development of computers and computing power is the computers get better and better at taking care of the tedium, but the kind of still the thing that really can't be like replaced by machines is some level of human understanding for those tasks which humans still need to carry out. So that's something that's worth developing, even if a computer can handle a lot of the calculation for you. More on that later. Then we'll do a little review of the central limit theorem, just to kind of generalize that binomial. And then finally, we'll go over confidence intervals. So confidence intervals, although they're the topic of this lecture, really only factor in at the very end, in a sense, although we'll still spend a lot of time on them. But the point here is that they flow really naturally from a good understanding of sampling distributions, especially the binomial, but also the sampling distribution of means, which is just as important. So let's review the binomial briefly. So the binomial distribution tells us that counts of successes for sample sizes larger than n equal to 1 actually look normal. And that's true even though the Bernoulli or the dummy or binary, they all mean the same thing here, distribution looks like a bar graph with only 2 possible values, and that's always true necessarily. And this generalizes to the distribution of regular sample means across many samples. So we're going to look at this important graphic one more time that I made in Stata. So what is this telling us? Again, what this is telling us is that when you have a sample of size 1, and so the possible numbers of successes are just the numbers 0 and 1, it doesn't matter how many times you take a large sample, that simulation that you're doing always is going to lead to this probability mass function that looks like the kind of abstract probability mass function that we can derive from first principles. Just thinking about what are the possible values of x here. So we've got 2 possible values, 0 and 1. And x, by the way, is a random variable here that means the number of successes. K generally is used to denote some specific observed number. So here we've just got 2 possible values, 0 and 1. And note that we can, come up with that on our own for, say, a coin. This represents basically a coin or any dummy variable where each outcome is equally probable. When we do all these many simulations, nothing really changes, right? So that's kind of the point, is that there's no gain here in a sense from doing these simulations. And by the way, we don't do these simulations in reality, right? But what we do in reality is we know that our sample comes from one of these sampling distributions, which we can simulate in Stata. And in some branches of statistics, it's more common to use these simulations. It's a procedure known as bootstrapping. That's actually how I make these graphs. But the point is that you don't actually have to do the bootstrap. Okay, so what happens when we increase the sample size? Well, then it turns out that any given sample has a count that comes from a distribution that looks normal. So for example, if we were to flip a coin 500 times and it's a fair coin, we know that the distribution of counts of successes, or heads in this case, although also tails because they're both equally probable, looks like this. And this basically looks like a normal probability density function. It's technically a probability mass function. You can see here, although it's a little bit hard to see, that there's these little ridges. So this is actually just a bunch of different bars, but you can see that it's starting to look really smooth, which is cool. But another point here is that basically as you get farther and farther away from the most kind of logical number that you would suspect from flipping a fair coin 500 times, for the number of heads, which would of course be 250. As you get farther and farther away from 250 in each direction, the probability of any of those outcomes goes down. And so what that means is we can draw a lot of conclusions about what a sample will look like if we know the true population probability of heads. We can say that samples like this are improbable, samples like this are probable. And later on, we won't think about actual numbers of successes because we'll be dealing with means, which are a continuous variable. So we'll be thinking about ranges instead. And what we can also do is we can say, as we'll see later on in this lecture, basically if we do have a sample, so we don't actually know the population probability, which we typically won't know. If we do have a sample, though, with a certain number of successes, we can fix a hypothetical value for the probability of the success and then say how probable is that under, how probable is our sample under this assumption about the small p probability of a success on a single trial. And if we get a big p binomial probability that's weird, given some value for small p, then we'll reject our guess for the value of small p. That's the idea of a hypothesis test. And I think it's actually a little more natural to introduce that first. In all honesty, I probably should have assigned the confidence interval and hypothesis test chapters out of order. But these ideas are very closely related, and we will talk about confidence intervals today. So the ideas are really closely related, and sometimes people overstate the differences between them, but there really is not much difference. So let's now talk about different ways of calculating binomial probabilities and some of the costs and benefits of calculating exact values. So what are the benefits of calculating exact values of binomial probabilities before we look at an example problem? First, we can derive the expression for the probability big capital P, or big blackboard P, which again is the binomial probability. It's the probability of a sample such as this by hand, and that's really cool. One of the drawbacks is that this is often computationally intensive, especially if we want to sum up the binomial probability for many different values of k. So for instance, probability of 0 through 40 successes, as we've seen in a previous lecture. In that case, we'll want to use the normal approximation or a calculator to solve because, as we've seen before, with the normal approximation, we can easily find areas under a curve which correspond to ranges of possible values. And as we saw in a previous slide just a moment ago, a lot of times the normal approximation is clearly quite good. So I'm going to show you 4 ways of doing this. The first way to do it would be to compute an exact solution by hand with the formula or plug it into Wolfram Alpha. The second would be to use Stata's binomial function, which takes 3 arguments and returns a capital bold P. In other words, it gives us the binomial probability, but we need to plug in values for n, k, and p. And note that this is a cumulative distribution function, not the probability mass function, so we'll have to be careful in how we use it. More on that later. You could use the online statistics book, or you could use the normal approximation, and we'll go through an example of each of these in just a moment. When you use the normal approximation, you can do this by hand with table A, which is a good thing to know, but you can also use Stata or the online stat book as well. So here's an example setup. In a nuclear reactor, special rods serve as a first-line defense against a core meltdown. Suppose a reactor has 10 control rods, each operating independently and each having a 0.8 or 80% chance of being properly inserted in the event of an incident. Furthermore, suppose that a meltdown will be prevented if at least half the rods will perform satisfactorily. What is the probability that upon demand, the system will fail? And here, I put up an example of a carbon rod. I wonder if the authors of this problem, Larson and Marks, by the way, who wrote a really good intermediate textbook called Mathematical Statistics, simply, were fans of The Simpsons because this is actually similar to several different plots in The Simpsons. So this is an example of such a rod being honored by reclusive billionaire Montgomery Burns in the show. But as fun as that is, let's turn to the math. By the way, some Easter eggs here if you are interested in seeing some excerpts, particularly funny bits from the episode from which this image is taken. You can click on those. So here's the way that we could solve this exactly. And as you can see, I kind of forgot to animate this, so there's a little preview there. Here's how we would do this, and ignore this for now. We'll let x equal the number of rods working correctly in a random sample, so basically some specific nuclear incident, and we want to find the probability that x is less than or equal to 4. Calculating it by hand would be a nuisance, but it's good to be able to see the exact expression. So small p, the probability of an individual dummy outcome, in this case where success means working correctly, so it's also a success in the conventional sense, p is equal to 0.8, n, our sample size, is equal to 10, and k here is going to take the values 0 through 4, so 5 possible values. And the reason for that is that we want to find the probability of a failure of the system, which would mean 4 or fewer successes. So we're going to say sum the binomial distribution for n equal to 10 and p equal to 0.8 from values k equal to 0 up to 4. And again, what do these components all mean? It's important to remind yourself of this fact. 0.8 to the k times 0.2 to the 10 minus k gives us the probability of some particular sequence of k successes and n minus k failures. For example, if we're trying to think of the probability of exactly 4 of the rods being successes, that means we'll have basically 4 of them having probability 0.8, right? And then 6 of them having probability 0.2. And you can imagine thinking about, okay, what if the first 4 succeed and then the last 6 fail? They're probably not arranged in a line, but you can kind of imagine that. So imagine them arranged in a line because this is a sequence. So that probability, 0.8 to the 4 times 0.2 to the 6, that would be the probability of the first 4 rods succeeding and the last 6 failing. However, that's not the only way for 4 out of the 6 to be 4 out of the 10, to be successes. So we need to say, multiply that by 10, choose 4, which gives us the number of different ways we could have those arrangements. And since each of those arrangements has an identical probability, we then just need to multiply that probability by the number of arrangements. Finally, that was only the probability for k equal to 4, so we would repeat the process for k equal to 3, 2, 1, and 0. And when we write this summation like this here, it's just conventional to put the smallest number on the bottom, largest on the top, but you can also think about it in the way I just mentioned, summing from 4 down to 0. Okay, so here's a link to entering the formula in Wolfram Alpha. This is how we would do it in Wolfram. I pre-filled this in for you here, but notice that you could change the numbers if you want. So if you wanted to change k to some particular value, you could do that. You could change 10 here, k here, etc. And note that Wolfram gives us the answer, and it gives us this very small probability of 0.0063 with rounding 6.4. So about a 0.5% chance of failure. That's pretty good. You could also plug and chug with the online stat book here, method 2. Let's examine that here. So we now need to change n to 10, and remember that some textbooks, as I warned you before, and I showed a couple of expressions involving this notation just for the sake of completeness, use pi not to mean Archimedes constant, but instead to mean the probability of success on an individual trial. So we fill this in with 0.8. And then now we need to find, there's a couple of different ways to do this, but probably the simplest way is to say just values below 5, which would be 0 through 4. Pardon me. So you can see here that we get basically the same answer that we just got when we plug this into Wolfram Alpha with rounding. Or you could use Stata. So Stata's only binomial function is actually for the CDF, but that's precisely what we want here, the cumulative probability of k successes or fewer. So the general syntax is this. It's display binomial NKP. And for the specific problem at hand, that would be display binomial. Remember, DI is just a abbreviation of display in Stata. Binomial 10 for 0.8. And we don't need to write anything in here to indicate that it's cumulative because, remember, Stata's function is the cumulative distribution function. So let's enter that into Stata. We should see the same answer. And we do. Awesome. So this is confirmation that we've calculated this correctly. So I wanted to turn and look at a bit of a complexity here. And let me pull this out for a second. So a brief comment on this. Using Stata for binomial calculation is actually not the most efficient tool. It's perfectly fine. And once you get the logic of it, it's almost exactly as fast. But it can be a little challenging at first. However, I think there's a couple of merits to learning how to do this in Stata. One, it's nice to have your workflow all in one place. So it's nice to be able to do everything in one program that you've been learning. And indeed, many pieces of software have similar limitations because they assume that the person using it is a relatively sophisticated user and therefore can use slightly kind of backwards ways of calculating things. And the programmers just kind of assume, well, why do we need to make it absolutely as simple as possible if it's already relatively simple? That may or may not be a good philosophy of programming, but that is the philosophy many times. So the second point is that this is actually also closely related to what we would do if we were using table A and we needed to use table A. And the connection is actually quite exact. Stata doesn't have a function for the binomial PMF, as I just mentioned, but we can exploit this simple relationship between the PMF and the CDF, which is what Stata's binomial function is. So the PMF at any value k is the value of the CDF at k minus the value of the CDF at k minus 1. You may want to meditate on that for a second. So let's discuss why that is. Remember that the CDF gives the probability of any value up until the point at which you're evaluating it. So the CDF at 4 gives us, as we saw before, exactly what we wanted, the probability of 4, 3, 2, 1, or 0 successes. So if we then subtract off the value at 3, or the value of the CDF at 3, that means that we're subtracting off the cumulative probability of 4, 3, 2, 1 minus the cumulative probability of 3, 2, 1. And both of those have zeros at the end, pardon me. So what that means is that you're just left over with the exact probability at basically 4 successes even. So we would write that in Stata like this. We would say display binomial 10 4.8 minus binomial 10 3.8, and that gives us this answer here. Why don't we actually briefly look first, and I'm going to start a fresh Stata session here. Let's briefly look at the online stat book, and let's see if we can calculate it exactly. We'll delete these other windows too. So we'll have 10 here, probability of 0.8, whoops. And then between, we can just say 4 and 4. And we should get the answer 0.0055, or about a 0.5% chance. Let's pull up Stata. And we'll say display binomial 10 for 0.8 minus binomial 10 3 0.8. And then we'll look at the answers, and we see that we get the exact same thing, which is reassuring. So you might notice that that's very much like using the cumulative distribution function that we get in table A for a problem with the z-score, right? If we wanted to find, say, the probability of a normally distributed variable having values between 2 points, we would convert them to z-scores, find the cumulative distribution function for the larger of the two, subtract from that the cumulative distribution function value for the smaller of the two, and that would just be our answer at the end. So this is actually identical to that problem of finding the area under the curve between 2 points effectively. The only difference is that in one case we've got a truly continuous variable, as in z-score problems, and here we've got a discrete random variable account. So I wanted to call attention to one more complexity here. So what if you want the probability of something like 5 or more successes? This again turns out to be basically identical to the same procedure that we use when we use table A. So if table A gives us probabilities of a particular input or one smaller than that, we just use the complement rule and we find 1 minus the probability of, in this case, 4 or fewer. So we would say display 1 minus binomial 10 for 0.8, and we would get this number here. We could have also just found the probability at the outset here, right, of this, and then what we would do is then subtract that from 1, but we could also just immediately do it in stata like this. So this is just saving you one step. So finally, let's take a look at the normal approximation. This gives us an alternative that points forward how we'll use the central limit theorem generally, which is we'll use the normal probability density function. We're going to break our rule here about when the normal approximation works, and you'll see that it's not a very exact approximation, but that's okay. If we tell you that you're allowed to use it on a particular problem on a homework, say, or a quiz, you're allowed to use it. So what's the mean of this distribution here, our binomial distribution? Well, we can calculate it as follows. We have NP. So remember that the mean of the binomial distribution, pretty intuitively, is the number of counts implied by the count implied by the probability of a single success, which is here 0.8, multiplied by the sample size, 10. So we just get 8. And the standard deviation, remember that we derived this last time, we've got a situation here where we've got a random variable, which is really the sum of a bunch of other random variables. So each trial is a random variable, and then the random variable x that keeps track of the counts is also itself a random variable. So when you add up all those other random variables, it turns out that if they're independent of each other, which they are here, the variance of the composite random variable is just the sum of the variances when the variables themselves are unrelated. And then to get the standard deviation, we just take the root of that. So the square root of the variance of a dummy, which is p times 1 minus p, and then multiplied by the number of random variables, so n, turns out to be 1.26. And the way we would do that is we would have 10 times 0.8 times 0.2, then take the root of it, that's 1.26. Then we're going to go ahead and calculate this in stata, and we'll use the normal cumulative distribution function, which works exactly like that binomial cumulative distribution function. It gives us the probability of basically, in this case, z-scores that are less than or equal to that one. Here, I didn't even go ahead and put in the z-score. We could do that, so let's find the z-score. So we'll say display 4 minus 8 divided by, gotta put parentheses here, 1.26. That gives this z-score here, and then we'll take that and plug that into the equation or the function, and we'll get the same answer back, right? So 0.008, or sorry, 0.0008. So notably, this is fairly different to the answer that we got before, right? Before we said we had about a 0.5% chance. Here we have not even quite a 0.01% chance, right? Or sorry, a 0.1% chance, pardon me. So it's fairly far off, but note that the normal is only a loose approximation here, and the exact answer is less than the next possible value of k, which is 5. So if we try plugging in here, let's just do it like, we'll do this actually. So if we do like this and plug in 5, plug in 5, note that we get an answer that's actually higher than the correct answer. So the normal approximation is not too bad since we plug in a value here that's the next possible value for a binomial, since that only comes in whole number amounts, and the next answer is too large. So we've kind of triangulated it in a sense. And this is what we get from using the online stat book. And again, how we would plug that in here, we could either plug in the z-score to the standard normal, or we could exploit the fact that this will take any normal and just change the mean and standard deviation, and then we do this here. Oops, sorry, just like that. Cool, so that's the normal approximation. So I wanted you to now think about this as a case of a hypothesis test. So how often do we know the probability of something like rod reliability with complete certainty? We rarely do. What we do have access to, unlike in this problem, is sample data. So in this case, we're thinking of a situation implicitly where we would have a hypothetical nuclear event. But what would be, and we happen to know the true reliability of the rod. But what if we're thinking about a more common situation where we just observe some event And then we want to use that to make inferences about the true underlying population probability, small p. So what if we did observe a failure? Does that provide evidence against the claim that p is equal to 0.8? So the traditional way of thinking about this is that it does provide fairly strong evidence against the claim, and this h naught here means our null hypothesis, that p is equal to 0.8. And before I just notated this as p naught, meaning that this is a hypothetical value, but you can also just state the null hypothesis, and then you don't need the naught on the p. The null hypothesis part is encoded in this language. Again, we'll introduce that soon enough. So what would that look like here? Well, note that this is too small to even see on our normal approximation here. So what that means is that this would be an event that if the true p is 0.8 occurs pretty infrequently. So it does provide evidence in this traditional way of thinking about things that the true population probability of a single rod failing is 0.8. Likely it's succeeding is 0.8. Likely it's lower, i.e. the failure rate is high.
So I want to now summarize the principle of the central limit theorem, which we discussed in the past lecture, but which is important to review the basics of before we discuss confidence intervals. So the basic idea is this, and I'm going to put it in just one slide. Even if a quantitative variable's distribution for individuals is skewed, its sample means sampling distribution is approximately normal. And this is also true for counts, as we saw in the case of the binomial distribution. One brief word before going further. So the sampling distribution concept itself can be challenging. What does it mean? It means basically if you could take 1,000,000 or 1,000,000,000 possible samples, what would the distribution of the means look like? What would the histogram look like? And we can go one better, and we can actually derive the exact form. So not just an approximation from 1,000,000 samples, or a simulation as I've called it, but we can actually just abstractly derive the form. And we already did that in the case of the binomial distribution. Pardon me. Sorry, I'm a little sick as I record this. So this can be known mathematically without even needing to do these simulations. The sampling distribution of sample means x bar is centered at the true population parameter mu. The standard deviation of the sampling distribution is given by sigma over the square root of n for some concrete sample size n. And we call this standard deviation the standard error. And as mentioned before, the intuition for why this is the standard deviation of the sampling distribution is pretty intuitive. So here's the kind of simple proof. Basically, we have a bunch of independent random variables that each individually are draws from a distribution with standard deviation sigma, just some standard deviation that is shared by all of them. They all come from the same distribution. We're assuming here that the population is very large so that these individual draws don't change the standard deviation, which in practice is a fine assumption. And note that in kind of classical statistical theory, where we're thinking about like rolling a fair die or flipping a fair coin, there's no, you basically don't have, you do have replacement, so you can re-choose the same option again, so it's not even a consideration. So then how do we come up with this actual estimate of the standard deviation of the sampling distribution, aka the standard error? Well, we can add up all those variances. And so we're going to add up the variance for all those variables. But we don't just have a sum of variables, we actually have a mean. And so we have the variance of the sum of a set of random variables divided by n. And you can factor out constants from a variance, but you have to square them when you factor them out for simple algebraic reasons that don't need to be reviewed here. So the variance is 1 over, pardon me, sorry about that. Basically, we have the variance of n random variables with standard deviation sigma over n squared, and then we add up all the variances, so that's sigma squared times n. So one of those n's cancels, and we have that the variance is equal to the standard deviation squared over n. And then to get the standard deviation, we just take the root of the whole thing, and we have sigma over root n. All of this becomes truer as n gets larger. So in practical terms, the standard cutoff is 30 for means, which is quite small. Here's an illustration. I've shown this illustration many times before, but again, just to hammer the point home, I'm so sorry about this. I don't have time to edit all this out, but I'm having a bit of hay fever. So on the left here, we have a simulation. Basically, we're presuming that a subset of the CPS, which is a very large sample, is our population. And we're pretending that's the population of a small city. Actually, the CPS is bigger than many cities, so this is not wildly off base. Then I pulled 500 random subsamples of the mean wage, and I did that 10,000 times. And in this simulation here, this is what the histogram of all of the means looks like, and you can see that it looks very normal, even though this distribution is evidently not normal. That's the central limit theorem. And the power of this theorem is that we don't need to do this replication. I'm doing this because I'm teaching this class, and I'm showing how this works. But in reality, you do not have to do this. You can just know that a sample mean is taken from this distribution, which is very cool. So one thing that we can do with this fact is we know that a certain proportion of samples fall within, plus or minus, a certain number of standard deviations of the mean. So a given sample comes from a sampling process that gives a sample mean that is within, say, 1.96 or about 2 standard deviations of the sampling distribution of the true mean 95% of the time. I know that was a mouthful, so let's take that one more time. So a given sample comes from a sampling process that gives a sample mean that's within about 2 standard errors of the true mean, mu, 95% of the time. That's just a fact about normal distributions applied to a slightly different situation. So if we add about 2 standard deviations of the sampling distribution, and we'll just call that the standard error mostly from here on out, I'll occasionally remind you that that's what the standard error is. So if we add about 2 standard errors to our sample mean x bar, we get a range including mu for 95% of all possible samples. This is that idea illustrated. So you can see here that the authors of our book simulated doing that. This is a very handy graph. And the idea is that because 95% of these red dots are within plus or minus 2 standard deviations of the true mean mu, that means adding 2 standard deviations on the sampling distribution to the red dot, so like here, subtracting and adding, here, subtracting, adding, here, subtracting, adding, we'll have mu somewhere in there 95% of the time. It's a really cool idea when you think about it. This is the idea of a confidence interval. So here's the intuition laid out in a little more detail, though. So the central limit theorem tells us that sample means sampling distribution is normalish. We just reviewed that idea. So if we wanted to know the true population mean, which might be something we're interested in, we could say that C% of all sample means fall within this range. But we don't know mu, right? So we don't actually know mu, and we can't say C% of all sample means fall within these 2 numbers. What we do, though, know is if we don't have, let me say that one more time. What we do know, even if we don't know mu, is that there's a C% chance that a sample mean we get will be within some range. So there's a 95% chance that it'll be within plus or minus 2 standard deviations of the true mean, mu. There's about a 90% chance that it'll be within, say, 1.6465 standard deviations of mu, etc. If we can calculate that range, which we can easily do, we get a plausible range of values for mu, which is better than nothing. That's pretty cool. So here's an example similar to that of the books, which I made in Stata. Note here that I presume that we know mu. The point of this is to show that even if we didn't, our range would still be a fine guess. So what's happening in each of these 4 examples here is we know the true population mean mu. We're using our Springfield data here. Then what we do is, in each case, we obtain the sample mean. In this case, it's this here. In this case, it's this here. It's this here, which looks similar to this, but it's not quite the same. And here it's this. And then we add and subtract that margin of error, as we're going to call it, which is the standard error times some critical value, as we'll call it, which is just a number of standard deviations. So here, for instance, we found the standard error for this distribution. Then we, pardon me, add and subtract 1.96 times that standard error. And you can see that in each of these cases, we capture the true mean somewhere in there, even though if we only knew the sample mean and not the true population mean mu, we wouldn't know where we are relative to the true mean mu, but we know that the true mean mu is probably somewhere in our bounds. So here's the logic of the recipe. Remember from table A that the standard normal probability density function, that normal curve, the bell curve, has x-axis units of standard deviations since sigma on the standard normal is equal to 1. So we find out, using table A or software, how many standard deviations include C% of the area under the curve. This is pretty routinized, so we'll very often use 95% as our level of confidence, which is what C% is. Those just mean the same thing. Sometimes we'll use 90, sometimes we'll use 99, but this isn't something that we're going to spend a lot of time messing around with because this part's pretty standard. The important part is our sampling distribution likely has a mean mu and a standard deviation sigma that are not 0 and 1 respectively. In other words, the sampling distribution is normal, but it's not the standard normal. So what we do is we just multiply the number of standard deviations z star, also denoted z sub c in these slides. They mean the same thing. I think z sub c is clearer, but our book uses z star. So we multiply by that number of standard deviations, which we get from table A, by the actual size of the standard deviation of our sampling distribution, which is given by sigma over square root of n, and again, that's called the standard error. Then we just add and subtract that to and from our estimate, x bar, and we get the following formula. So a confidence interval with confidence c is equal to x bar plus or minus z sub c times standard deviation of the individual variable over root n, and this gives a standard deviation of the mean. Here's the actual recipe without all the theory. Now you should understand the theory, but if you do want a set of steps to follow, these are them. Pick a level of confidence C. 95% is standard if arbitrary. You generally can't go wrong with this. Find out the number of standard deviations from the mean, whose AUC is equal to C. Multiply this critical value, denoted z star, or in my notes, z sub c, by the standard error, the standard deviation of our sampling distribution, to get a range of plausible values from the mean. And pardon me, add and subtract this resulting number, which is called the margin of error, to our estimate in order to get that range. Here's an example. So the GSS includes an interesting variable which tries to quantify the respondent's socioeconomic status. Is that a kind of quixotic view of socioeconomic status, that it can be turned into a numeric value? I think so, but it's kind of interesting, so let's play around with it. Let's suppose, for simplicity, that the sample standard deviation S is equal to sigma, the population standard deviation. That's simplifying and it's a little unrealistic, but we'll come back to that problem in a couple weeks. If this were true, what's our 95% confidence interval? So now let's go ahead and solve the problem. So our first step is to pick a level of confidence. We can pick any old number. Let's use 95% for simplicity. Remember, we don't know the mean of the sampling distribution. It is mu, and we don't know that. We're trying to guess it. But we do know that C% of sample means fall within, plus or minus, some critical value, standard deviations of mu. And I'll just call this z sub c, or z, for short, with the implicit idea that you know that it's some specific z that corresponds to c. And so we're just going to use this picture of the normal curve that we've used before. We're picking an area under the curve here, which corresponds to some level of confidence, and then we're going to find out, if we don't already know, what the associated z is. Now in this case, we happen to know z, but we might not, depending on the level of confidence. So our next step, whether we our next step, if we don't know z, and in principle, I'm just saying this in a general way, so even if you already know z, you might come across a situation where you don't know it. So the next step is to find what critical z goes with c. We can use table A for this, or stata, which is easier. Let's try stata, actually, since we've been using table A, but I want to have you all start using stata a little bit more for this thing. Here's the syntax, and I'll explain where the syntax comes from in a moment. We say display inv norm, or inverse norm, 1/2 times 1 minus the area under the curve you want as a decimal. I know that seems like a lot. I'll explain why that is what it is in a moment. It's actually really important, and you can't get out of this. So even using table A, you actually need to use this exact logic. We're just speeding it up with stata. So for example, to find the area under the curve that has 95%, to find the z-score that has an area under the curve of 95% associated with it, we would write display NV norm 0.025, which gives negative 1.96. That's a critical value for a 95% confidence interval. Now, technically speaking, there's always two critical values, but they're just negative 1 times each other, so you don't need to do this twice. Just say, okay, it's negative 1.96, the positive version is 1.96. And we could do that using table A as well. So for instance, we could look in table A and see, okay, we're looking for, in this case, is the positive half of the table. So we would look and say, okay, where's 97.5? It looks like it's right here. That's 1.9 since I'm in this row here. And I go up and I'm in 6. So 1.96 is the right spot. But I think this is a little bit easier. And note that it's really easy to do this. So let's just go pick an arbitrary level of confidence. Let's say that we want to pick, let's say 64 confidence, right? Actually, let's pick something a little bit larger since we want to pick something realistic. So let's say we want to do like 92% confidence, okay? So what that means is we want to think, okay, what's the area under the curve? Basically, outside of that, it's 8%. And then what's half of that? It's 4%. So we're going to say display inverse normal 0.04, and we get negative 1.75, and nothing really to round here. So now let's check that using the online stat book. This is a good thing to bookmark. So this is the standard normal curve. So when we put in this answer here, we should get 92%. So we're going to say between this and then this here, and we get effectively exactly 92%. So this works for arbitrary areas under the curve as well. So why is the syntax what it is? Well, there's kind of two components. Both are explained by this fact. Table A and the normal functions data both list cumulative probabilities, so they are values of the normal cumulative distribution function for select Z. So if you just put in the area under the curve you want into the inverse function, or look in the table and then go out, you'll get a z-score that has the whole area to its left and twice that area outside of it in its additive inverse. Additive inverse is a fancy name for the normal function, for the negative version of a number. Also, the 1 minus, you might wonder, why do we do that in the first place? It ensures that we get the area outside of basically this, right? So if we just put in 95% here, we would get a z-score that's got 95% of the area under the curve to the left of it, which is not what we want. And then we would just subtract, so 1 minus 95% is 0.05. But then again, if we think about what happens if we do 0.05, we could just say display NV norm here, 0.05. I just realized that I already have this up. Note that what would happen here is that this gives us the value, the z-score, that has 5% of the area under the curve to the left of it, and then also 5% of the area under the curve to the right of negative 1 times this, because the normal curve is symmetric. So if we come here and look on the online stat book and we plug in negative 1.64 and 1.64, you can see that the area under the curve is actually only 90%, not 95%, because of that fact that I just mentioned. So here's another example. An 80% CI comes from this, display NV norm 0.1, and we can see that this checks out here. So why is it 0.1 for an 80% confidence interval? Well, in the first case, we would say we want not the 80% cumulative, but we want basically a z-score that's got 10% outside of it. But we can't just, 20% outside of it. But we can't just use 20% because that would leave 20% to the left and then 20% to the right of the negative version. So we chop it in half, and that gives us finally 0.1, and that's how we can come up with this. Okay, so that's how we would do that. Then we get the margin of error. So we now know the number of standard deviations for the standard normal for given confidence. And in this case, it's 1.96 and negative 1.96. How do we translate that to units of our actual variable? We just multiply z sub c by the size of our variable standard deviation, which is here the standard error, sigma over square root of n. And we call that specific quantity, when we do that multiplication, the margin of error. So in this case, we're going to take 1.96 and multiply it by the standard deviation, which I've already forgotten, but it's written down in the notes before. And hopefully when you're following along at home, you wrote this down. So it was 23.03, and then we would divide that by the square root of the sample size, which is 2248. Let me just show that. Probably should have put that in the notes. So we say display 23.03 divided by square root of 2248. And we get 0.48, blah, blah, blah. Then we're going to say display 1.96 times. We can just copy paste this. And we get, in this case, 0.952, 0 with rounding. So when we come back here, we see on the figure that I made that that's where that number comes from, right? So this quantity here, this is mu minus the margin of error. This is mu plus the margin of error. Now, we don't know what mu is, but the idea is that if we did know mu, then this would capture the middle 95% of the sampling distribution. Now, the nice thing is that even if we don't have a sample mean that's centered right at mu, we know that adding and subtracting this margin of error to our sample mean, if it's, say, over here, or if it's over here, or if it's over here, is going to capture mu in its boundaries. So what we do then is we just add and subtract that margin of error to x. So in this case, we do that here. This part's just arithmetic. And this gives us a plausible range for mu of the socioeconomic index. This is what that looks like. So here, I had Stata basically just pull for random samples here. You can see all of our x bars here. And this is a lot like that figure that we looked at before, except in this case, we're saying that mu is fixed because, pardon me, mu is variable because we don't actually know mu. In this particular case, we really don't know it. We just know the sample mean. So what I did here was I simulated situations where mu was, say, 46.75, or mu was 47.66, or mu was 46.39, or it was 47.19. Then what I had Stata do was pull a sample and then add and subtract the margin of error. And the idea is that we're going to land somewhere where, okay, we're not right on the true population mean, but we include the population mean somewhere in its boundaries, in this case, all 4 times, which sort of stands to reason because this should work 95% of the time. You could actually turn into a binomial problem, the question of whether or not you should expect 4 of them to have a single miss or not. But this is the idea, is that we should do pretty well. So we can also use our coin flips, and sorry, I wanted to animate this here. We could do this with our coin flips. So this is going to change the setting of the problem slightly. This is, we're going to use proportions here actually. These work a lot like means, so we don't actually do a lot of direct binomial confidence intervals, but we use something very close to the count of successes. We use the proportion of successes. So we'll use our coin flip example. This is a rare case where we know the population parameters. We know that the true mean of a fair coin that we all had was 0.5, and that was the proportion as well. So let's see how many people's confidence interval includes 0.5. For now, you can just accept that the standard error in this case happens to be 0.1. And using the proportion of heads that you got, you should calculate a 90% confidence interval for the proportion. So when I did this, I think I happened to get 14 heads. So what I would do here is I could do this in Stata, and I could say display in this case, so we have our sample mean, which would be 14 out of 25, so we'll calculate that. That's 0.56. So we say, okay, our mean is 0.56, and then we want to add and subtract to that basically the standard error times the number of standard deviations. Well, we found before, just by coincidence, that this happens to be the z-score for a 90% confidence interval. So we'll take this here, and we'll find the lower bound, which is this, and then we just said before we should accept at face value that the standard error is 0.1. So this gives the lower bound, which is 0.395. Let's round it to 0.4. So that's our lower bound for the estimate of the true population proportion of heads flipping a fair coin. And then we'll just do the same thing, but we'll add it like this. And we see that the upper bound estimate is 0.72. So that actually does include the true population proportion that we happen to know to be true in this case because it's just a physical fact. And here's what this looks like for all the examples. What this shows here is a sample proportion of heads on the y-axis, and then this is just a sample number. So we had about 93 samples from last semester and this semester. Last semester is the first time I did this particular experiment. And you can see that only people that happen to flip a very large number of heads or a very small number, I think this is 17 and this is 8 here, missed the true population parameter. But you can see that most intervals capture it somewhere in there, and actually this works even better than it should. We have just about 100 coin flips in this case, and we expected to miss the true population parameter about 10% of the time. We actually only miss it about 5% of the time. So we happen to have, and probably some of this comes from maybe a couple of people just saying, well, I should have gotten, maybe some people just filled in a number that sounded plausible. Or this might just be a rare case where we happen to have really good luck because this isn't a full simulation of the sampling distribution, far from it. So here's some advanced facts about confidence intervals. First, the standard error, and thus the margin of error, decreases as n increases. So that's an important fact. The standard error, and thus the margin of error, decreases as n increases. Think about the arithmetic of the formula here. So as we're increasing n, this entire quantity is getting smaller, this entire quantity is getting smaller, and then the entire range is getting smaller. But intuitively, basically what that means is larger samples are better, which you probably already knew. There's also, generally speaking, a trade-off between confidence, which is represented here by this z-score, and precision, which is the size of the overall range. Again, arithmetically, as z increases, which means that you're taking a larger area under the curve, so does the range. This is getting bigger. Intuitively, the more certain you are about some range of outcomes for a probabilistic event, the looser your claim has to be. So for example, if I say, no matter what, when I wake up tomorrow, the world will be in a nuclear war or not, that is true. That's not very useful information, right? Conversely, if I want to say something really precise, I generally speaking need to make smaller claims. So for instance, if I'm looking at my dog right now, she's sleeping near me, and she's looking up at me very funnily, I can say, well, I can guess with almost absolute certainty that she'll need to go outside and use the restroom one more time before I go to bed. But that's kind of a trivial claim, and it's a claim about something I already have a whole bunch of knowledge about because I've lived with my dog for almost 10 years. So it's not actually that interesting of a claim vis-a-vis me making a claim about something that I might have a scientific interest in as opposed to a kind of loving, familial interest in. Now, I wanted to end with a few caveats, as I often like to. A lot of times the devil is really in the details in statistics. So here's a ubiquitous mistake that people make when they interpret confidence intervals. I want to ward you off of it, not just to be pedantic, but because this gives you a better sense of what exactly a confidence interval is. So here's a wrong interpretation of a confidence interval. The confidence interval gives the bounds for 95% of all possible sample statistics. Here's the correct way to say it. The procedure has the population parameters somewhere in a given range 95% of the time, and informally, we are 95% confident that the true population parameter is within the lower bound and the upper bound. The reason that this here is wrong is that this would require the sample mean to be the true population mean. This is a statement that we could make if we knew mu. And sometimes in these slides, I've given you the impression that we do know mu because I'm trying to show that this works when we do know mu. We can verify that it works. But in practice, we don't know mu. We're guessing it. So even though we've shown some simulations where we happen to know mu to prove that this works, we often won't know it. And when we don't know it, this statement is wrong unless we happen to get the true population parameter as our sample mean just by coincidence. But that's highly unlikely. So there's two layers of uncertainty in a confidence interval. First of all, our sample mean might just be really weird and our confidence interval fails to capture the population parameter. That's represented by this situation here. But even if our sample isn't especially atypical, the boundaries of a confidence interval are A, a range, so they're not an exact number, and B, they're somewhat arbitrary because we selected Z, and we selected that based on an arbitrary level of confidence. So really, there's like 3 layers in a way, so you should always be careful about confidence intervals. They're just rough interpretive guides. Here's some extra thought questions to help all of this sink in. Calculating standard confidence intervals is pretty monotonous, and many researchers who report 95% confidence intervals may misunderstand what they actually mean. So let's be better and tackle some challenging cases. Let's say you arbitrarily want a 72% confidence interval. What is Z sub 72? Here are some hints, and these get progressively easier. First, you could draw a picture of the standard normal in shade C. The next page has my own hand sketch of this. Or you could find 1 minus C over 2 with arithmetic. And then you could use table A or NB norm to find the Z associated with this. And here's the actual code. So how do we get this code here? Well, we wanted a 72% confidence interval. That means that we want 28% of the area under the curve to be outside of this, and we want 1/2 of that, or 14% of the area under the curve, to be to the left of it. That finally gives us a value that we can plug into this inverse cumulative distribution function. So we plug in 0.14 and we get negative 1.08. If you did want to draw that picture, and by the way, we can check our work here, so let's do that now. So we want here between negative 1.28 and 1.28. And you can see that this is, wait, sorry, I had 1.28 in my head. It's 1.08. 1.28 was from before. Okay, so now you can see this is 72%. So how would you draw a picture? This is the kind of hand sketch you might make to solve this question. Now, I don't show a lot of these anymore because I got better at programming after starting to teach this class, and my handwriting is pretty atrocious, but it does require some programming finesse. So if you are just taking this class, as probably all of you are, I would recommend always drawing a picture like this and then thinking about it backwards. Pardon me, sorry. I have another thought question here. I realize these slides got a little bit out of order. So here's the other thought question. So is it 100% confidence interval possible? If so, why or why not? Here are the hints. What z's encapsulate the entire area under the curve? Technically speaking, the curve extends over the entire real numbers. We've learned that before. So 100% confidence interval would actually be meaningless. Intuitively, all we can say with complete certainty is that the mean exists somewhere on the real number line. So now finally, I did want to first put these slides in order. Sorry, you're getting to see the rough draft here. Finally, go ahead and look at some actual concrete examples of interpretations. And we'll actually go ahead and delete these here because we don't need these anymore. So let's practice interpreting these. So this is a very famous paper about the reversal of health outcomes among white working class, well, not just working class, but it turned out to be worse among the working class, white non-Hispanics who were, middle-aged when this paper came out in 2019. So you can see here that the authors, Case and Deaton, first found the mean days that physical health was not so good in 1997 to 1999. Then they found the mean in 2011 to 2013. And the confidence interval for the change here, the raw figure that they got was 1.18. But they took a confidence interval for the change. So that was between 1.11 and 1.24. What they did was give us a plausible range of values. Now, this might seem kind of trivial, but what if we had a giant standard error and they estimate 1.18, but the standard error was something like, let's say it was exactly 1/2. So then if we take that 1/2 and we multiply it by about 2 to get a 95% confidence interval, that means we should add and subtract 1 to this And then at the lower bound, the difference could have been as small as 0.18. That would not be very significant, right? So by putting up this confidence interval, we're not so much focusing on these bounds here, which is one reason you sometimes only see the margin of error reported. What we're doing is we're just saying, what's the rough range of values? Like, what are some kind of outside, values that capture the biggest and smallest plausible values? And you can see that they did the same thing here for a variety of different outcomes, like neck pain and so on. Here's an example, another health example. I just happen to have a lot of examples from when I taught health. This gives the prevalence of chronic disease and disability among men and women in the United States, England, and Europe, more on the health reversal story. And you can see here that this gives for the United States, England, and Europe, white, black, kind of gray and black here, the prevalence of heart disease, stroke, hypertension, etc. And you can see again that, by the way, these are confidence intervals for proportions. It gives us a sense of basically, okay, so they measured in the sample prevalence of heart disease about 18%, but what is a plausible range of values? And it was pretty tight, maybe 19 to 17%, something like that. By the way, the fact that these error bars don't overlap here, or they do overlap here, does not actually give us a sense of whether or not these bars differed from one another. This is another extremely common misinterpretation of confidence intervals, but we'll discuss that a later week. Here's another one. These are age-standardized death rates for the range of ages 40 to 74 by level of education in 3 male cohorts. This is basically Moscow, St. Petersburg. This is some health center there, Helsinki, and then Oslo. And so if we look at this, we can see, note that what they tell us here is these are doubled standard errors in brackets. And what these are death rates basically for these three places in the low, middle, and high education groups. Why do they have doubled standard errors? You might want to pause and meditate on that. The reason that they put doubled standard errors there is that doubled standard errors are also margins of error approximately for a 95% level of confidence. And so we can basically kind of craft our own confidence intervals by adding and subtracting these quantities to these here. It's a little bit of what my old stats TA, Joshua McAuliffe, who's actually a UW graduate student now, used to call beer math, kind of as a joke, right? The idea is doing 1.96 in your head times something pretty hard, but 1.96 is awfully close to 2, and 95% is a commonly used confidence interval. So if you have a standard error, just double it and then add it and subtract it from to and from, respectively, the sample mean that you got, and that'll give you what you want. Here's a couple more, confidence intervals to practice. This one has a lot going on here, but you can see what this is basically doing is giving the average distance and standardized test scores between the 90th and 10th percentile families across a variety of studies, across a variety of years, and this is just giving you a sense of how big the gap is. So here are some confidence intervals in the wild, and we can see that these are all about really interesting topics, and they help us get a sense for what values are plausible as opposed to what was just the sample mean observed in the study. That's something that we haven't actually discussed so far, and hopefully it's interesting to know that we can actually come up with a plausible range of values using pretty simple arithmetic techniques. Thanks for watching. See you later.